Electricity is a fundamental part of our modern world. It powers our homes, our devices, and even our bodies. At the heart of all electrical systems are circuits. A circuit is a closed loop or pathway that allows electricity to flow. Imagine a circuit as a racetrack for electrons, the tiny particles that carry electrical charge. Just like a racetrack guides cars along a specific path, a circuit directs the flow of electrons. Circuits are made up of various components connected by conductive materials like wires. These components can include power sources like batteries, resistors which limit current flow, capacitors which store energy, and many others. The way these components are arranged and connected determines the type of circuit and its behavior. Understanding the different types of circuits is essential for anyone interested in electronics, from hobbyists to professionals. Two of the most fundamental circuit types are series circuits and parallel circuits. These two configurations form the basis of more complex circuits found in everything from simple flashlights to sophisticated computers. In a series circuit, the components are connected one after another in a single continuous loop. Imagine a string of holiday lights where each bulb is connected in a line. If you were to follow the path of the wire, you would find that it passes through each light bulb in sequence before returning to the power source. This inline arrangement is the defining characteristic of a series circuit. The current, or flow of electrons, has only one path to follow. It moves through each component in turn, like a train traveling down a single track. This straightforward design makes series circuits relatively simple to build and understand. However, it also means that the functionality of the entire circuit is dependent on each individual component. If one component fails, the entire circuit breaks, just like a single burnt-out bulb can disrupt the entire string of holiday lights. To understand how series circuits work, we need to consider two fundamental concepts: current and voltage. Current is the rate at which electric charge flows through a circuit, while voltage is the electrical potential difference that drives this flow. In a series circuit, the current remains constant throughout the circuit. This is because the electrons flowing through the circuit have only one path to follow. They must pass through each component in sequence, and the rate of flow remains the same at any point along the circuit. Voltage, on the other hand, is divided among the components in a series circuit. The total voltage supplied by the power source is split proportionally across each component. Imagine a water pipe with multiple constrictions. The total water pressure is distributed across each constriction. Similarly, the total voltage is distributed across each component in a series circuit. This division of voltage is an important characteristic of series circuits. It allows us to control the voltage across individual components, which is useful in many applications, such as dimming a light bulb or controlling the speed of a motor. Unlike series circuits, where components are connected in a single line, parallel circuits offer multiple paths for the current to flow. Imagine a river splitting into several smaller streams that eventually converge back into the main river. Each branch represents a separate path for the water, and similarly, each branch in a parallel circuit provides a separate path for the current. In a parallel circuit, the components are connected across each other, forming parallel branches. This configuration allows the current to split and flow through each branch independently. If one branch of the circuit is broken, the current can still flow through the other branches, unlike in a series circuit where a single break interrupts the entire flow. This redundancy makes parallel circuits more reliable than series circuits, especially in applications where a continuous flow of electricity is critical. For example, the electrical wiring in our homes is primarily designed using parallel circuits. This ensures that if one appliance fails or a circuit is overloaded, the other appliances and lights in the house continue to function. Section 5. Current and voltage in parallel circuits. The behavior of current and voltage in parallel circuits differs significantly from that in series circuits. In a parallel circuit, the voltage across each branch is the same. This is because each branch is connected directly across the power source, experiencing the full potential difference. Current, however, is divided among the branches in a parallel circuit. The total current drawn from the power source is split proportionally among the branches, depending on the resistance of each branch. Branches with lower resistance allow more current to flow, similar to how wider pipes allow more water to flow. This division of current in parallel circuits allows multiple devices to operate independently at their required current levels. For instance, in a house wired with parallel circuits, each appliance can draw the current it needs without affecting the current available to other appliances. Section 6. Ohm's Law, the foundation of circuit analysis. Understanding how current and voltage behave in series and parallel circuits is essential. However, to analyze and design circuits effectively, we need a tool to quantify these relationships. This is where Ohm's Law comes in. Ohm's Law, named after the German physicist Georg Simon Ohm, describes the fundamental relationship between voltage, current, and resistance in an electrical circuit. It states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. This relationship is often represented by the following simple equation: V equals Y times R, where V is voltage, measured in volts, I is current, measured in amperes, and R is resistance, measured in ohms. Ohm's law is a cornerstone of electrical engineering, providing a fundamental understanding of how electrical circuits behave. It allows us to calculate the current flowing through a circuit, the voltage drop across a component, or the resistance required to achieve a specific current flow. Section 7. Applying Ohm's law in series and parallel circuits. Ohm's law can be applied to both series and parallel circuits, albeit with some key differences. In a series circuit, the total resistance is simply the sum of the individual resistances, as the current has to pass through each resistor in sequence. Therefore, the total resistance in a series circuit is RT equals R1 plus R2 plus R3 and so on, where R1, R2, R3, etc. represent the resistances of the individual components. In a parallel circuit, however, the total resistance is calculated differently. This is because the current has multiple paths to flow through, and the total resistance is actually less than the resistance of the smallest individual resistor. The total resistance in a parallel circuit is calculated as follows: 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. By combining Ohm's law with the specific rules for calculating total resistance in series and parallel circuits, we can analyze and design circuits to meet specific needs. Section 8. Real-world applications, series and parallel circuits in action. Series and parallel circuits are not just theoretical concepts, they are the building blocks of countless electrical systems we encounter every day. Understanding their applications can provide a tangible grasp of these fundamental circuit types. Series circuits, due to their simplicity and the voltage division characteristic, are commonly used in applications where a single power source needs to power multiple components with lower voltage requirements. For example, a string of LED lights often employs a series circuit. Each LED might require a specific voltage lower than the supply voltage, and by connecting them in series, the voltage is divided appropriately across the LEDs. Parallel circuits, on the other hand, are extensively used in applications where a constant voltage is required across multiple components, and their independent operation is crucial. The most common example is the electrical wiring in our homes and buildings. Appliances, lights, and other devices are connected in parallel, ensuring a constant voltage supply to each device while allowing them to operate independently. These are just a few examples, and the applications of series and parallel circuits are vast and diverse, ranging from simple household appliances to complex electronic devices. Section 9. Series versus parallel, choosing the right circuit type. Both series and parallel circuits have their own unique characteristics, advantages, and disadvantages. Choosing the right circuit type for a particular application depends on the specific requirements of the circuit. Series circuits are simple to design and build, making them cost-effective for applications where multiple components need to be powered by a single power source. However, their limitations, such as the dependence on each component for the circuit's functionality, and the equal current flow through all components, make them unsuitable for many applications. Parallel circuits offer greater flexibility and reliability, with the ability to operate even if one branch fails, and the ability to provide a constant voltage across multiple components. However, they can be more complex to design and wire, especially for circuits with a large number of components. Ultimately, understanding the behavior of current and voltage in series and parallel circuits, along with their respective advantages and disadvantages, is crucial for anyone working with electrical circuits.